One of the most amazing things about our universe is its immense size. It's almost impossible to imagine just how vast it is. However, this immense size can also be quite disappointing. Imagine if we used our powerful telescopes to discover another Earth-like planet in a distant galaxy that's perfect for human life. The sad reality is that it would take us centuries to get there. For individuals today, leaving our galaxy is simply impossible. Everyone knows that Earth is located in the Milky Way galaxy. The closest galaxy to us is the Andromeda galaxy, which is about 2.5 million light-years away. Even if we could travel at the usual speed of a spacecraft, about 28,000 kilometers per hour, it would take us an astonishing 94.5 billion years to reach Andromeda. Even if we could travel at the speed of light, it would still take 2.5 million years to get there. This is incredibly disappointing. What's the point of discovering all these new planets if we can never visit them? But what if there was a shortcut to travel beyond our galaxy? A shortcut that could let us travel millions of light years in just a few months. This is where things get interesting. These shortcuts are called wormholes. Consider the 2014 film Interstellar. In it, Cooper and his team leave Earth to find habitable planets. They travel through a wormhole, moving from one galaxy to another in mere minutes. This wormhole, discovered by NASA near Saturn's orbit, is key to the movie's plot. The fascinating thing is that wormholes aren't purely science fiction. They are grounded in real science, specifically Einstein's theory of relativity. While their existence remains theoretical, wormholes offer a tantalizing possibility for future space travel. They could be the shortcuts we need, potentially making intergalactic travel a reality. So, what are wormholes exactly, and how can we use them? Let's delve deeper into Einstein's theory of relativity to understand the intriguing concept of wormholes. When Albert Einstein formulated his theory, he expressed it through a set of equations known as Einstein's field equations, which he first presented on November 25, 1915, to the Prussian Academy of Sciences in Berlin, Germany. These equations, comprising 10 intricate nonlinear partial differential equations, but in short, they can be represented by only one equation. And that equation looks something like this. This describes how matter and energy influence the curvature of spacetime. Albert Einstein suggested that we visualize spacetime as a big mesh. When you place heavy objects on this mesh, they cause it to bend. Similarly, spacetime curves around massive objects like planets and stars. The greater the gravitational force of an object, the more spacetime bends around it. While Einstein introduced this concept, he couldn't fully solve his field equations. The first person to do so was Carl Schwarzschild in 1916. His exact solution described how spacetime curves around a single massive object, leading to the theoretical understanding of singularities and black holes. If a mass becomes infinitely dense, the curvature of spacetime wraps so tightly around it that this region pinches off from the rest of the universe, forming a black hole. Decades after Schwarzschild's solution, the first photo of a black hole was captured in 2019. This showed that black holes were theoretically understood nearly a century before they were observed. Interestingly, another solution to Einstein's field equations is the concept of wormholes. Just as quadratic equations can have multiple solutions, Einstein's equations are complex and can yield various solutions. Wormholes, scientifically known as Einstein-Rosen bridges, were proposed by Einstein and his assistant Nathan Rosen in 1935. Wormholes can be thought of as shortcuts connecting 2 points in spacetime. To illustrate this, imagine a flat piece of paper with 2 points, A and B. The shortest path between them in 2 dimensions is a straight line. However, if you bend the paper into a third dimension, you can create a much shorter path by bringing A and B closer together and piercing the paper. Similarly, in our three-dimensional space, the shortest path between distant galaxies like the Milky Way and Andromeda is millions of light-years long. But if space is curved into a fourth dimension, a much shorter path could potentially exist. It's hard for us to imagine the fourth dimension since we live in a three-dimensional world. However, by comparing two-dimensional and three-dimensional spaces, we can get a better understanding of how wormholes might work. This is a world map and want to fly from Delhi to New York. You might think the shortest route is a straight line over Africa. But in reality, the shortest route is over Finland, Sweden, Iceland, and Greenland. This path seems longer on a flat map but is shorter when you consider the Earth as a sphere. In 1957, scientist John Wheeler published a paper on Einstein-Rosen bridges, using a similar analogy. He described a worm eating through an apple. The worm travels a shorter distance by going through the apple rather than around its surface, like airplanes travel around the Earth. Wheeler named this concept a wormhole. When you search for wormholes online, you'll find many diagrams showing 2 points connected through a hole. Imagine a space-time mesh with an object that has extremely strong gravity. This gravity bends space-time so much that it pierces through to the other side, creating a shortcut, similar to folding a piece of paper and poking a hole through it. However, wormholes work in 3 to 4 dimensions, making them difficult to visualize. In reality, if a wormhole exists, it would look like a spherical ball. As you enter, everything around you would curve, and if you look back, the Earth would appear to be moving away. This concept was depicted realistically in the movie Interstellar. As of 2023, wormholes remain a theoretical concept derived from Einstein's field equations. While they provide fascinating possibilities, their existence has not been proven. In movies, scientists have tried to visualize wormholes. Many theories exist, but no one has seen a wormhole yet. Scientists aren't sure if they really exist. However, if wormholes do exist, they could function as time machines, allowing you to travel millions of light years in just a few minutes. This means you could reach a destination before light does, effectively jumping through time. If wormholes are real, the first question is how to create their openings. This requires an extremely strong gravitational force. The answer lies in black holes, as theorized by Einstein and his assistant, Rosen. Black holes have the necessary gravitational pull to open wormholes. Everything would be attracted to the black hole and flow through the wormhole tunnel. But what's on the other side of the tunnel? If there's another black hole, there would be no way out. You'd be trapped. For a wormhole to be a viable tunnel rather than a trap, there must be something on the other side that is the opposite of a black hole: a white hole. White holes, like black holes and wormholes, are another theoretical solution to Einstein's field equations. A white hole is the opposite of a black hole in every way. Instead of pulling things in, a white hole pushes things away, creating an exit point from the wormhole. This theoretical concept completes the idea of a wormhole being a bridge through space-time, allowing travel from one place to another. While white holes have been proven theoretically, just like black holes and wormholes, they remain unobserved in reality. In black holes, light can't escape once it's trapped inside. In contrast, in white holes, light can't enter. It can only be emitted, making them extremely bright. Russian physicist Igor Novikov first used the term white hole in 1964. Scientists say a white hole is like the reverse of a black hole. Just as nothing can escape a black hole's event horizon, the point of no return, nothing can enter a white hole's event horizon, a boundary of no admission. Objects inside a white hole can go out but can't go back in. Although white holes are a theoretical solution to Einstein's relativity theory, no one knows how they form in reality. Black holes form when a star collapses on itself. But what could be the opposite process? Some scientists think the universe emerged from a giant white hole during the Big Bang. Another idea from Stephen Hawking suggests that black holes eventually evaporate due to radiation, leading to a massive explosion. If this happens, what about the matter and information inside the black hole? Quantum theory's no-hiding theorem states that no information can be lost. If black holes expel all the matter and information they suck in, it might happen through a white hole. Based on this, some scientists think a white hole forms when a black hole dies. However, we don't fully understand how black holes die yet. Some scientists argue that white holes can't exist because they would decrease entropy, violating the second law of thermodynamics. This law states that entropy or disorder in a system can only increase. Black holes increase entropy by consuming everything, leaving only radiation. Despite these arguments, some scientists believe white holes exist. In 2006, the Neil Gehrels Swift Observatory recorded an event GRB 060614 that some think was a white hole. It saw a bright light explosion that quickly disappeared. Usually, such gamma-ray bursts occur when a black hole swallows a star, but no star was found in this case, suggesting it might have been a white hole. However, this hasn't been seen again, so white holes remain theoretical. But black holes were once just a theory too, until they were proven. The same can be said for wormholes. Even if they are proven, scientists doubt humans could travel through them. Interestingly, in 2015, scientists created a magnetic wormhole in a lab. They used special materials to separate a magnet's poles, creating an invisible gap, a magnetic wormhole. This device let the magnetic field of one magnet travel through one end and come out the other, similar to how a space-time wormhole would work. They achieved this using a high-temperature superconducting material called yttrium barium copper oxide, cooled in liquid nitrogen. Even if we don't prove wormholes exist, we might find other ways to travel faster than light. One idea is the Alcubierre drive, proposed in 1994 by physicist Miguel Alcubierre. This concept involves a spacecraft traveling faster than light by contracting spacetime in front and expanding it behind. This is another theoretical solution to Einstein's field equations. It will be interesting to see what practical applications can come from these theories. So friends, if you liked this video and learned something new, please like it and share it with your friends.